Welcome to my lecture, BIM and the Life Beyond the Building Site. My name is Michael O'Shea and I'm a researcher in UCC. And today I'm going to give a short lecture on a selection of potential applications for BIM beyond construction. So before I do that, I'd just like to go over a few, I suppose, concepts in BIM, and the first one being, what is BIM? I often hear the phrase "a single source of the truth," and what does that mean? Well, my interpretation of what that means is the truth is the common data environment, and the common data environment is a repository for all the data relating to a building, be it drawings, specifications, schedules, etc. And it's populated by a number of collaborators, or all the collaborators on the project, ideally being the client, the engineer, the architect, the main contractor, subcontractors, facility managers, project managers, etc. And I think that's well defined in terms of design and procurement and construction phases. So in terms of BIM, how design and how 3D design and Revit has all taken over in terms of designing a project, going into the procurement phase, and how that is outlined in a BIM environment using the EIR, etc. And also in construction, how contractors can now feed back through the BIM process by producing their own submissions during tender stage, to collating quality documents and uploading schedules and costings in the BIM. I think that's quite well defined. But what happens after the building is completed? Um, Ideally, you have a rich BIM with all the building related data, be it drawings, models, updated models, as-builts, all the equipment manufacturing information. So what happens after it? How do you utilize such a tool, such a data rich tool? I think that question is probably important for facility managers, clients, of course, and also engineers, main contractors, subcontractors, project managers, suppliers. Theoretically, at the end of the building, the end of the defects period even, they kind of fade to the background unless they're undertaking new projects related to the asset. So as well as defining what BIM is, I think it's important to go through the different types of levels before we get into the meat of the presentation. So BIM level 0 is probably what the construction industry has been for the last 20, 25 years. Two-dimensional CAD drawings, an unmanaged process. And by unmanaged, I mean it was quite linear in terms of a client specified what they wanted, a designer, architect undertook drawing specifications to meet those requirements, and that was sent out to tender, whereby a contractor built those with very little collaboration in between those phases. So BIM level 1 is still probably at that level in terms of collaboration. There isn't much collaboration, maybe between the codes in terms of electrical and mechanical, in terms of 3D design. But BIM level 2, BIM level 1, I guess, in terms of the Irish context, we're probably between BIM level 1 and BIM level 2 at the moment. BIM level 2 is a mix of 2D and 3D design, so very much going into the 3D element of design and models. COBie, building information, and building data. But I guess the key difference is collaboration. So there's a common data environment, which is the first mention of that, and the single source of truth, I guess, is manifested in this common data environment, whereby all the different designers, architects, produce their models, 3D models, or their data, and they contribute to a federated model, which is a model made up of all these different entities. But it is federated rather than being a unified model. So it's first step on the path along the road to the truth, I guess. In BIM level 2, which is now mandated in all UK projects, government projects above a certain value, as well as several other European countries. We're not there yet in Irish terms, in terms of public projects. The dimensions, I guess, related to BIM level 2 are programming, or time before dimension, so how the project develops over time and scheduled. And also the fifth dimension, which is cost. And this is where quantity surveyors come into play, and where I guess their skills are utilized in BIM, and how elements and different ways of constructing things are priced into the BIM, and how different elements and materials are used in the BIM. And I guess BIM level 3, whereby the goal is in the next 5 or 10 years, that's where we'll be operating in the industry, utilizing transactable interoperable data. That means everybody is working off the same data types and data formats. So IFC, for instance, you're probably familiar with the IFC data set. And in those terms, In terms of dimensions, that goes to 6 and 7 and 8D, and they have all different definitions. Generally accepted that 7D is facility management, or 6D is sustainability, and then you have 8D safety. But depending on what institute and where you are, those dimensions are defined differently. For now, 3D, 4D, and 5D are quite clearly defined because a lot of jurisdictions are working in BIM level 2 and up to 5D, I think is fair to say, where BIM level 2 is at the moment. So in terms of BIM level 3 and 6D, 7D, etc., what I'm going to focus on is facility management. So how can we utilize a rich BIM in facility management where once the building is built? And this comes into play in terms of repair and renovation, space management and occupational comfort, and operation and maintenance of the building, how it's operated, and how that feeds into sustainability goals. So how do you manage waste? How do you manage energy? And how do you reduce your carbon footprint ultimately? So a couple of case studies I'm going to look at involve structural health monitoring, building environmental monitoring, and also live sensor integration or live data uploading in the BIM. The first study I'm going to look at looks quite basic on the outset, but it's quite a clever study. So what the researchers did is they created a scale model building, and they inserted wireless sensor nodes, which are accelerometers. They created an algorithm to detect local damage from these sensors based on vibrations, and they fed that data into a remote server wirelessly. So this is the actual model, the physical model. It's intended to represent a 4-story building, and they've created a digital twin of that in a Revit environment. So that's all quite straightforward. But the key thing and what the theory they tested was, could this be undertaken using the existing IFC schema? So in a BIM level 3 environment, can this be done in an interoperable manner? And they found they had to make amendments to the IFC schema, extensions as they call it. So that's quite a simple premise. It's important for the industry to move forward that that type of work is being done in the semantics. In a more tangible way, I guess, applications of BIM in the facilities management or the structural health monitoring area. Recent work has been looking at a concrete bridge and integrating the structural health monitoring. So in this aspect, looking at how to represent spalling of that asset on a BIM. So, well, quite a simple application. It's very useful and very worthwhile, because generally with these bridges, they get inspected for every 5 or 10 years, and if this data is being collated in such a visual manner, it's very easy to identify errors and structural integrity. So also as part of that work, they looked at spalling in girders and how they could affect and how they could impact flexural reinforcement in the girders. So here you can see different types of flexural reinforcement and shear reinforcement being damaged. That's all collated in a BIM environment. So it's making use of a BIM after the construction stage. Taking that one step further is to integrate live data into that, or live sensor data into such a BIM. So this is a steel railway, self-sensing railway bridge, as it's called, and in reality, the bridge was there was several strain gauges inserted into the bridge girder beams, and these were represented then virtually in a BIM environment and given all their structural parameters as well as their geometric parameters, but also the data collection parameters. And this was then fed into a BIM in real time using visual programming, which we'll talk about a little later. And they developed a color coding system to identify strain. So this is levels of strain. And you can see that this is real time updated in this bridge, the level of strain, which is quite a useful tool for anyone operating loads, or if these are taking freight, what type of freight loads and what impact that has on that bridge or that asset. So it helps with the long-term maintenance as well as the structural health monitoring. A very smart, intelligent use of BIM after or post-construction. So I've mentioned kind of graphical programming and how that's undertaken. So Dynamo is what I use, and it's one of the open source packages that's used with Revit. What it actually is a graphical programming interface. It enables automation, integration, and processing of data in the BIM environment. And in our case, the data is sensor-driven data. So the data we collect from sensors, we use Dynamo then to process it and integrate it within a BIM environment and to visualize it. It's quite easy to use from an engineer's point of view. It's visually orientated, so it's made up of a series of nodes and elements and different code blocks with different functionalities, and you essentially have your functionalities and you link them to your other functionality. So it's a very nice way of using graphical programming rather than writing reams and reams of code. So one nice use of sensors and BIM is in building environmental monitoring. So in this case study, the researchers created a BIM of a classroom, and they inserted several sensors. These are sensors down here: temperature, humidity, and CO2. So they actually have 4 campus buildings. This is a university, and they undertook the trial in one of the rooms with a view to extending it. So what they did was they created a digital twin, or a virtual world, virtual representation of the sensors, and then using Dynamo and another Firefly, which is another visual programming tool, they created 3 algorithms to identify comfort, energy saving, and how the building or how the room met the wellness standard. This was they then created a visualization layer to visualize the results and fed this back into the Revit model so it could be visualized. So in essence, what they did is they defined a zone where body temperature sensitive range, and they used their sensors to identify when that could be achieved. The ultimate goal of this project was how to utilize open windows and air conditioning, and ultimately to reduce energy consumption. So they represented this is the room in the BIM. So it's the same room, just represented in different times. So from 5 o'clock when the window was open, moving along when the window was closed at 6 o'clock, and then moving along to when the actual air conditioning kicked on. So you can see the different levels of temperature in the room and humidity. So it's so then this is fed into a decision support system, which tells the air conditioning to turn on or the windows to open or close. So a very smart tool integrated in the BIM using live sensor data. And this is how they achieved it, using Dynamo, or yeah, it was Dynamo. So they created, they had a code block to import the live sensor data. This was then processed to visualize both temperature and humidity, and then integrated into the BIM to visualize in the actual room how it would be visualized. And from there, that data was then taken into the decision model about whether to open a window, close a window, or turn on the air conditioning. This was then fed back through the loop. So while it looks very complex, it actually is. If you break it up into its constituent blocks, it's quite an easy logic to follow. So this brings me on to my own case study, which is the Kish Lighthouse. Sorry, it's an area that I've been studying for the last couple of years. Came about when a building information model, or a Revit model, was developed to undertake a lot of remedial works about 4 years ago. Since then, we've taken it on and expanded that Revit model into a level 2 and possibly at this stage a level 3 BIM. In terms of the dimensions, not particularly with interoperable data, because we are quite refined in the data we're using. So the Kish Lighthouse itself is about 11 kilometres offshore of Dunleary in Dublin. It takes quite a lot of punishment from the Irish Sea in the wintertime. The Kish Lighthouse itself is a quite unique build. It was a telescopic tower build. So initially a foundation caisson was built, a reinforced concrete foundation. And within that, a tower unit was constructed, which hosts 7 or 11 levels, living quarters and operational quarters. It was then, so once the tower and the caisson were built, they were floated in one unit and shipped out to the site of the Kish Bank. It was then sunk into place, and from there, the the tower unit was actually floated from within the caisson and grouted into place, and this area was backfilled with sand, so it created a composite structure, and that's important for later on. So one of the first activities we did with the BIM to enhance the existing BIM was to document the various inspection reports, which span 1960s to the 2010s. I think 2015 was the latest inspection report. So we collated all the damage detection and gave it a color coding based on severity, and also a shape based on the type of damage that had been incurred. And what we actually found from visualizing or putting these all into the BIM was that there was quite a concentration of damage in an area that we didn't expect. So this is above the water line and to the lee, so it's in the least exposed area. So there's quite a collection of damage in this area, which was an interesting finding. Now we're still collating the damage reports and visualizing it and looking for ways to analyze that. So allied to that, I guess the the more important work we're doing is looking at the structural issues in the kit. So there's two primary structural issues. There's a stability issue whereby it has been reported in several storms when the lighthouse was attended that the tower rocked. So what we want to establish first of all and foremost is the tower rocking as a whole structure from base to top, or is there differential rocking between the tower and the basement section, this annulus, i.e. is the annulus failing, which would be quite a serious issue. A slightly interrelated issue is a pressure signal. There's quite a large water pressure build-up underneath the caisson, which is theoretically sealed, so should not have any pressure build-up. It should just be residual water. And this pressure signal, as I'll show later, is showing a tidal signal. So that's quite a worrying phenomenon. So given that we had a BIM and we have an interest in sensors, we decided to place a lot of sensors on the building, as well as link external sensors such as wave and tidal sensors that are not necessarily on the building but related to the building in a BIM environment. One of the first results we got was actually, one of the first results we actually got was comparing the water surface and the pressure signal within the tower. So the bluey grey signal is the pressure that we recorded on our sensor, and the tidal signal is the tide inside and Dublin Bay. So there's quite a distinct pressure signal getting in here. So that's an area of concern at the moment that we're hoping to look at further over the winter. But what we've ended up with is a range of external sensors. So that's a Dublin Bay buoy, a LiDAR sensor. We also have an in-situ wave gauge, which we're hoping to install this year, which will give us real-time data at the structure. We've installed a pressure sensor, and we've also installed accelerometers and geophones in anticipation of a winter where we should see some rocking, hopefully. All the sensor data is then collated wirelessly through the internet into a remote database, which is within our BIM environment, and it's where our Dynamo script starts to take place, starts to act. So that's my cue to show you the actual BIM. So this is the model that we have created. I've taken out the walls just to show you the sensors for the time being. So here, this is a geophone sensor that we've modeled. And what you'll actually see is, we're just modeling on cuboids, but what you'll actually see is we have this area here where we have live data coming in. So this is based on live data. So we have accelerations coming into the model. Likewise, we have our pressure sensor modeled. It's a little bit slow. We have a pressure sensor modeled here, and here we can bring in live pressure and the date stamp it. So that's good for visualization, but I guess for the BIM, what we really want is to collect the data in the environment. So as well as within the BIM, we have we have time series of the pressure, the geophone. We also have other sensors linked up. I'm just showing these for brevity. So that's where we are with it, and how we actually undertake that is bringing live sensor data into the BIM. Is through Dynamo. So this is the Dynamo script that I'm using at the moment, that I've developed, and I'm by no means a coding expert. In fact, I'm far from it. But a couple of days using Dynamo, and it's quite intuitive. So you set a file path, so the file path just reads off the data files that are downloaded from our central server, where all the sensors upload the data in real time. And then it goes through a series of code blocks to actually get out and be displayed as scheduled. So the plan for the next, I guess, installment of this research is to actually visualize ways of visualizing the data. So we're collecting the data and scheduling it at the moment. The next, I suppose, jump is how to visualize it. So like they did in that case study for the temperatures in the room, we want to be able to visualize the data and how it interacts with the sensors. That's our next step, I guess, in where we are. Just to wrap up, I guess another use we found for our BIM model is, I guess it's probably unique to our own facility. We do a lot of wave tank testing, and given that there was a lot of discrepancies about the stability of the tower. So from the initial design report in the 60s, in 1963, to stability reports in the 80s, and most recently a finite element analysis model in 2015, they all had different factors of stability. So what we decided to do was to examine the stability ourselves by developing scale models. So we actually 3D printed physical scale models from the BIM We trialed it at a 1 to 200 scale first of all, and we've subsequently developed a 1 in 60th scale model of the actual lighthouse using the BIM, and we're hoping to test that in our wave tank over the coming months, whereby we'll establish what the factor of safety is for the scale model, and we'll feed that back into the BIM model as well as another element of I guess added value in the BIM. So in conclusion, I hope I've shown you, I guess, where BIM will go in BIM level 3 in the next 5 to 10 years, what we're looking at in terms of after the building has been completed, how we can increase the value and increase the capability of BIM using these tools such as visual programming and also wireless sensors and live data. One thing I didn't touch on is the Internet of Things, and I think the Internet of Things and BIM will coalesce in a big way in the next 5 to 10 years. So that's my presentation. I hope it provided some insight into where BIM is going. If you have any questions, just I guess use the forum, or alternatively, you can email me. It's Michael O'Shea at ucc.ie. Very easy. Okay, thank you very much.